In today's class, we are going to find eigenvalues and eigenvectors for a 2 cross 2 matrix. Okay, so first we are going to consider the matrix. So the matrix here is 5, 2, 2 and 2. A 2 cross 2 matrix we just take. Okay, so what are these eigenvalues and eigenvectors is? It is a square matrix. Okay, so you can see the matrix which we have considered should be a square matrix. So for eigenvalues and eigenvectors, AB will be equal to lambda B. Okay, what does it mean is you have a matrix. A is a matrix. It is a square matrix. When this matrix is multiplied by a vector. Okay, so vector you can, you know that it is a one-dimensional array, right? So here when you are multiplying a matrix and a vector, you can represent it with a scalar. Lambda is a scalar. Okay, so lambda into V, a scalar into a vector. Okay, so this will be a mathematical definition for your eigenvalues and eigenvectors. So here A is a square matrix, V is the eigenvector and lambda is the eigenvalue, which is a scalar value. Okay, so first for this matrix, we are going to find what the eigenvalue is. So how do you find the eigenvalue is? Generally, an eigenvalue is found by the equation determinant of A minus lambda I is equal to 0. So on solving this, what do we get is, we get a equation. For a 2 cross 2 matrix, it would be a quadratic equation. It is named as a characteristic equation. Okay, so to find the eigenvalue, we are going to solve the equation determinant of A minus lambda is equal to 0. So the equation, final equation, whatever you get, it is a quadratic equation in case of a 2 cross 2 matrix, and that matrix is named as the characteristic equation. As I told you, this is a quadratic equation. You will have two roots for it. Those roots are named as your eigenvalues. The other name for that eigenvalue is your latent roots. Okay, so your eigenvalue is also named as latent roots. Okay, so we will get into the problem and check how to solve the problem. Okay, so determinant of A. A is nothing but the given matrix 5, 2, 2 and 2 minus lambda. Lambda is the eigenvalue which we are going to solve the equation and find. Until that, it will be kept as lambda itself. I is the identity matrix and the order of this identity matrix is nothing but the order of A. So here the order of A is 2 cross 2. So for I also it will be a 2 cross 2 identity matrix. Okay, so it will be 1, 0, 0, 1. Okay, so the whole thing you have to equate it to 0. Okay, so now it will be determinant of whatever is inside the bracket, we are just going to, so normal subtraction only. Okay, so it will be 5, 2, 2, 2 minus lambda is multiplied inside. Okay, so it is lambda, second term lambda into 0, lambda into 0, lambda into 1 equal to 0. So this will be equal to determinant of 5, normal subtraction, so it is 5 minus lambda. Next term would be 2 minus 0, so it is 2. Next term it is 2 minus 0, 2. Next one, 2 minus lambda. Okay, so this should be equated to 0. Okay, so if you observe A and A minus lambda I, what you observe is only in the diagonal the term is subtracted by lambda. So you can avoid the steps and you can directly write this as determinant of only the diagonals. You can write it as 5 minus lambda, 2 minus lambda. The rest of the terms you can write as it is. Okay, so this is equal to 0. Now we are going to solve the equation. So determinant means these two terms minus these two terms. Okay, so it is 5 minus lambda into 2 minus lambda minus 4 is equal to 0. Okay, so when I expand it, I'll get 10 minus 5 lambda minus 2 lambda plus lambda square minus 4 is equal to 0. Okay, so now coming from the higher power, first is lambda square, minus 5 lambda minus 2 lambda would be minus 7 lambda, 10 minus 4 would be plus 6 is equal to 0. So now you can see that it is a quadratic equation. So how do you find the roots is the product of the two numbers, it should be 6 and the sum should be minus 7. So two numbers which satisfy this are, if I take minus 6 and minus 1, when I multiply minus 6 into minus 1, I'll get plus 6. Minus 6 minus minus 1 will be minus 7. So I can write it as lambda minus 6, lambda minus 1 is equal to 0, or I can write lambda is equal to 6 comma 1. So these are called as your eigenvalues or latent roots. And this equation which we got on solving the determinant, this is called as your characteristic equation. Okay, so now we have done with the eigenvalues. Next we have to find what the eigenvectors are. So how do you find the eigenvectors are? Eigenvectors are found by using the formula, the same formula which we at the beginning we saw as the definition. AV is equal to lambda V. So when you're taking lambda V to the other side, you'll have AV minus lambda V is equal to 0. So first two terms as V as common. So I can write it as A minus lambda into V is equal to 0. Okay, so lambda is a scalar and A is a matrix. So scalar and matrix subtraction wouldn't be possible. So we have to write it as A minus lambda I into V is equal to 0. Okay, so for our problem, A was nothing but 5 to 2, 2. Okay, so now we are going to write what is A minus lambda I into V is equal to. So as I told you, when I have A minus lambda I, only the diagonals will be subtracted with lambda. Okay, so A minus lambda I would be nothing but 5 minus lambda to 2 minus lambda. Okay, so now when I rewrite this equation, it will be 5 minus lambda to 2 minus lambda into the vector. So here each column, okay, vector wise if I am seeing, I have 2 columns, right? Sorry, 2 rows I am having. So here again my vector will have 2 rows. Okay, so I will name it as x and y is equal to 0. Okay, so now this will be the general equation. So now for this equation we will find what the eigenvectors are. So this eigenvectors would be based on the corresponding eigenvalues. So the lambda value which we got earlier was 6 and 1. So when you are writing your eigenvalues, write it in the descending order. Write the bigger one first, then the smaller one. Okay, so here since we have 2 eigenvalues, we will have 2 cases. Okay, so first case when lambda is equal to 6. Okay, so lambda is equal to 6 would be substituted in this equation. So when lambda is equal to 6, what will happen? 5 minus 6. So I'll get minus 1, 2, 2. 2 minus 6 is nothing but minus 4 into xy is equal to 0. Okay, so while you find the roots, what will happen is you'll have minus x plus 2y is equal to 0. And the second equation, it will be 2x minus 4y is equal to 0. Okay, so when you observe both the equations, equation 1 and 2, what you can notice is when you multiply 1 with minus 2, the first equation with minus 2, what will happen is you'll get it as 2x minus 4y is equal to 0. So you can see equation 1 and 2 will become same. Okay, so when you have the same equation, so you cannot solve and get different x and different y. One would be depending upon the other. So from equation 1, from 1, you will have 2x is equal to 4y. Okay, so suppose x is equal to 1 means what will happen is 2 would become 4y, or y would take the value 1 by 2. Okay, so now your vector would be represented as 1 and 1 by 2. See, since you are having 1 by 2, what you can do is you can multiply it throughout by 2 to bring down the fraction to a normal term. Okay, so this would be approximately equal to, when I multiply by 2, the first term would be 2 and the second term would be 1. Okay, so when lambda is equal to 6, the corresponding eigenvector would be 2 and 1. Okay, so now after this what you have to do is you have to normalize the vector. I just named this vector as v1. You have to normalize the vector. Okay, so v1 we got it as 2 and 1. We are going to normalize it. So normalizing means it is nothing but v1 divided by norm v1. So how do you find the norm v1 is nothing but it is square root of each and every term. You have to square it, sum it. So it will be 2 square plus 1 square, which is root 5. Okay, so normalizing v1, what you get is 1 by root 5, and here you'll have 2 and 1. Okay, so this is when your lambda is equal to 6. Next you are going to find when lambda is equal to 1. Okay, so when lambda is equal to 1, your general equation was 5 minus lambda to 2 minus lambda into the vector was equal to 0. So when lambda is equal to 1, what will happen is I'll get it as 5 minus 1, which is 4, 2 minus 1 is 1 into xy is equal to 0. So now again you have 4x plus 2y is equal to 0. Next one, 2x plus y is equal to 0. So again when you observe equation 1 and 2, if the second equation is multiplied by 2, you will get it as 4x plus 2y is equal to 0. So both are equation. So you will not get different values for x and y. One will be depending on the other. Okay, so taking the second equation, I'll have 2x plus y is equal to 0, or I'll have 2x is equal to minus y. Suppose if I'm taking x is equal to 1, what will happen? I'll have 2 is equal to minus y, or I'll have y is equal to minus 2. New vector. So now my new vector v2 would be equal to, x is taking the value 1, then y is minus 2. Okay, so when you normalize it, normalizing of v2 is nothing but v2 divided by norm v2. So v2 is nothing but 1 minus 2, and this is nothing but norm of v2 is nothing but 1 square plus minus 2 square. So it is 1 minus 2 divided by root of 2 square is 4 plus 1 5. Here you have got two eigenvalues. You arranged it in the descending order. For each eigenvalue you had a corresponding eigenvector where you finally normalized and you found what the eigenvectors are.